Welcome to this video where we take a look at how we transform the molar flow variable. In chemical engineering, we generally deal with mixtures of a lot of fluids, and we try to differentiate these mixtures as a form of molar fractions. Now, when doing calculations in these molar fractions, what happens is that we work with restrictions. Generally, this would mean that the sum total of all the mole fractions should add up to 1, and the mole fractions of every single component should not range outside of 0 and 1. Now, what happens is that generally we're trying to solve for the mole fraction of a certain component, and as the number of components in a mixture gets larger, the calculations become more and more complex. So we might even have to deal with a set of nonlinear simultaneous equations. So in order to make these calculations easier, what we can do is transform the mole fraction variables. In this particular example, what we're going to do is we'll transform our mole fraction variable into this expression right here, and we'll take a look at how we can do our calculations from there. So let's get started. So we have our first equation, which says that the mole fraction of a component I is equal to e raised to the power of our variable vi divided by 1 plus summation from 1 to n minus 1 e times vi. And this is true for I that is less than n. We have another expression which says xn is equal to 1 minus summation of n minus 1, it's starting from 1, xi. Now, let's take a look at where we can go from here. We see that xi is actually equal to this expression, so let's do that substitution in this equation. So our xn ends up being equal to 1 minus summation of 1 plus summation of e raised to the power of vi in the denominator, and in the numerator we have e raised to the power of vi. Now, if we calculate this particular summation, what we'll realize is that it's actually a constant. So this entire denominator is a constant, because of which we can take this outside of the outer summation. So what this would look like is xn equals 1 minus 1 over 1 plus summation of e raised to the power of vi times summation of e raised to the power of vi. If we simplify this form, what we get is 1 plus summation e times e raised to the power of vi minus summation e raised to the power of vi, and the whole thing is divided by 1 plus summation e raised to the power of vi. Now we can see that these two terms in the numerator cancel out, and what we end up with is xn equals 1 over 1 plus summation e raised to the power of vi. Now what we can do here is that let's bring this term to one side and the rest on the other. So multiplying on both sides, we get xn plus xn times summation e raised to the power of vi equals 1. So we have xn summation e raised to the power of vi equals 1 minus xn. And therefore, we end up with this final expression that says summation of e raised to the power of vi is equal to 1 minus xn divided by xn. So we get this expression. Now what we see is that in our original equation, we have the same exact term. This is actually also ranges from 1 to n minus 1. So let's see what we can do from here. So if we do a substitution in this equation, what we'll end up with is xi equals e raised to the power of vi divided by 1 plus 1 minus xn divided by xn. Now let's keep simplifying these terms. We get xi equals e raised to the power of vi. Whole thing is divided by xn plus 1 minus, oh, let's erase that. Pen 1 minus xn, and the whole thing is divided by xn again. Again, these two terms cancel out, and we have, if we multiply this to the other side, we get xi over xn equals e raised to the power of vi. Now, what we can do is, if we take the logarithm on both sides, ln xi over xn equals natural log of e raised to the power of vi. Therefore, we end with vi equals natural log of xi over xn, and this is valid for I less than n. So in this way, we can calculate vi from xi and xi from vi. This way, the calculations become a lot easier, and instead of having to deal with multiple simultaneous equations, we can simply calculate the mole fractions in Python or other computation methods through this equation.